1 to any power is, what's 1 squared? What's 1 to the third? What's 1 to any power? 1. So yeah, it stays 1 no matter what x is. So if a is 1, then it's y equals 1, which is a pretty boring function. Well, I don't want to judge, but it's not that exciting. What happens? And a must be greater than 0. What happens if a is equal to 0? It gets stuck at? No, if a is 0. What's 0 to the 0 power? 0 to the first, 0 to the 0. So it gets stuck at 0. So we're trying to find things that aren't lines. What happens if a is negative? Something else happens, right? So the point is, I'll leave that for Ms. Conroy to explain. But we're looking at a is positive and a can't be 1. We skip over 1. So let's take a look at this. So let's see what these look like here. It says graphing exponential functions. F of x equals 2 to the x. F of x is equal to 2 to the x. If you were going to go about graphing this, what's a great first thing for you to do? You could make a table, yeah. Plot points. It's interesting. No matter what math class you're in, if you're ever asked to make a graph, some people, there are systems like graphing quadratics. You look at zeros and you try to find curvature and things like that. But what can you always do if you're lost or just as a general good place to start? You can always plot points, make a table. I remind calculus students of that all the time. Like you can always plot a few points. Is it really helpful to have a couple points? Yeah, if you have no idea where to start with a couple points. What are some easy numbers to plug into just about any function? What's one number that would be really nice to plug into this one?
0.
Yeah, so what is f of 0 in this case? It's 2 to the, close. 2 to the 0 is 1. 2 to the 0 power is 1 by definition. So we could go over here, and what does that mean that point is? That point is going to be, plug in 0, get out 1. So we could go over here and we could plot that point. 0, 1. So 2 to the, oh, there it is. There it is. Nice. Say I plotted it right there. So we could continue making a table here. The x value and then the 2 to the x value. So it was 0 and 1. What's another x value I could plug in there nicely? Yeah, we could just make them whole numbers. Why do we want to make it whole numbers? Yeah, whole numbers is the end. Yeah, you get whole numbers as your output. Now, can you plug in any number you want for x here? Pretty much. Yes, you can plug in any number you want, actually. The domain is all real numbers. You can plug in anything you want. So we could say 2 to the first is, 2, and then 4, and then what's the next in the value? 8. So we could plot these values here. So you plug in 1, and what do you get? You get 2. Plug in 2, you get 4. And plug in 3, and you get 8. So we have this right here. We have this function right here. Yay. Now, does it stop right there at this point right here? Does it stop right there? Does it continue in a direction? It goes also to the left. What does it look like it's going to do? Is it going to spike back up? No, that would be a quadratic. It's not. So what's it going to do? Keeps going down. Now, how do we know that? Well, these numbers right here, we could also plug in a can't be negative, but can you plug in negative x values? Yeah, you can plug in negative x values. So let's plug in some negative x values. So if we plugged in -1, that's 2 to the -1. How do you rewrite 2 to the -1 to understand what that value is? What does 2 to the -1 mean? What does it mean? Yeah, 1 over 2 to the first, right? So that's just 1/2. So that point right there would be -1, 1/2. So hey, it's right there. Gets closer down. What about -2? What happens when I plug in -2? It's 2 to the, not 1, it's 2 to the -2. And what is 2 to the, that's 1 over 2 squared. So that's 1 over 4. So does it get closer and closer to the x-axis? Yeah, it does. Does it ever touch the x-axis? No, like you could plug in negative, thank you, Java, negative lots, right? If you did negative lots, right, negative, any big, huge negative number, it would be 1 over 2 to that big number. That gets closer and closer and closer to 0, but does it ever actually get to 0? No, it gets infinite. You can get as close as you want. So what does this graph end up looking like? Well, it goes back like this. Yay, like that. Does anybody know, you might have heard this word before, or maybe not heard this word before. What is this line called right here? That's the x-axis right there. It's also called something, and that's y equals 0. Can you ever get to that with this function? Can you ever cross it? No, it gets infinitely close. Does anybody know what that type of line is called in a graph like this? Begins with an A. Anybody? Just checking to see if you've heard it before. It's got a cool sounding name. Asymptote. You ever heard of asymptotes before? There's different types. Horizontal, vertical, and oblique. That is an asymptote. It gets infinitely close to it, doesn't cross it. Now, what about 5 to the x? Is there any difference in how we go about graphing it? No. So what's a great place to start? Plugging in x equals 0. So f of 0 is 5 to the 0, which is still what? 1. So this one will share a point with this one. Where's the only point it intersects? It intersects right here at 0, 1. But what's the difference about this function? What does this function do a little differently? It has the same type of shape, but what does it do differently? Yeah, you can use it. What does it do? Does it go up? Mm-hmm. How fast does it go up? Faster than this one, exactly. Everything's relative, right? So what's 5 to the first? Oh, that's 5, right? What's 5 squared? Well, way up there, right? So what does this one look like? It goes up really steep. And then on the other side, does it stay above the blue or below the blue on the other side? Does it go above the blue or below? So like right here, it goes below because when you do a table, let's do a table here. Let's just do a few values. So we have x and 5 to the x. How about -1, 0, 1, and 2? Well, that's 5 to the -1, which is 1 what? 1/5. And this is 1, and this is 5, and this is 25. So this actually goes down below right here. Does it do the same thing? Does it ever touch the x-axis? No. You can think of gravity is stronger on the base and it goes up faster. It's like the rocket's going faster. So all of these exponential functions, a to the x, they share one point because a to the 0 is what? 1. So they're all going to share that point right there. Does ever say negative infinity, so you do like this to this? You want to see another way to do it? Another way is this. X, such that x is contained in the real numbers. There's all different ways, but whatever you're told to do, I know, it's crazy. Whatever you're told to do, stick with this. Also, you can always say all real numbers. What's the range, by the way? What's the range on this? What's the range? What are the outputs? All real numbers greater than 0. So you have what? 0 like this, 0 infinity? Because can it ever be 0? No, and it goes up. Are any of the outputs negative? No, it never goes below the x-axis. So you do have this handout in your notes? Yeah. So try this one for me. Graph that. So you started with maybe an x value of 0. Yeah. So you have x, and then you have 1/2 to the x, like that. So maybe you started with 0, so you had 1/2 to the 0 is what? Oh, it's 1. So we're still starting at 1. So maybe 1, 2, and 3. So then you have 1/2 to the first, 1/2 to the second, 1/2 to the third. So what is that? 1/2, 1/4, 1/8. Is that right? I think that's right. So yeah, zoom in as far as you can get here. So you know it's going to be what? 1/2 and then 1/4. So what is it going to do over here? Go down, kind of like a reflection of what we just did. So then you don't want to ignore the other side. So maybe plug in negative what? -1. Well, that's 1/2 to the -1. What does that equal? That's 2. It's 1 over, or what's another way to write? Let's do it this way. I like this instead. 1/2 is 2 to the -1. What's 2 to the -1 to the -1? It's just 2 because you multiply the powers. So that's 2. What do you do with -2? Well, that's 1/2 to the -2, which is the same thing as 2 to the -1 to the -2, which is 2 what? 2 squared. And that's equal to 4. So do you want to guess when you plug in -3? What do you get out if you want to guess? It's 8, yeah. So you're going to end up with 2 going to, -1 going to, what is it, 2? -2 going to 4, and -3 going to, oh, that's not high enough, 8. Oh, so do you get a curve that looks really similar? You get a curve that looks very similar to what you just had. So if the a value is between, what's the difference here? If the a value is between 0 and 1, it's going to be a reflection over the y-axis. It's going to be a reflection over the y-axis. Like if you took this right here, if you took this graph right here, and you just duplicated it, so we're going to paste this right here. Where's paste? Come on. Oh, man. Where's... Oh, there it is. Thank you, like this. And it put it all the way down there. Why does it do that? I don't know why it puts it there sometime. And I'm going to take this. I think there's a rotate, right? Let's see what it says. Let's rotate right 100 and then rotate again. Whee! It's fun doing the transformations. Rotate again. Rotate right 90 degrees. Oh, did it go again? Man, I'm just Let's rotate. Man, there we go. So if you took this right here and brought it all the way up to the other side, see this right there, cut. Can't really bring it up here. I'm trying to do it, but it moved it. What's it going to look like if I pasted it out? It's kind of look like the opposite going up like this, right? That was what? That was y equals 2 to the x. And what's this one right here? Y equals 1/2 to the x. So it's kind of important to see that. They're reflections of each other. They're reflections. Okay, so what are the common characteristics of the graphs of all of them? What are some of the common characteristics for all of them, regardless of A? They have the same domain. Yeah, the domain is going to be all real numbers. And what else? The range is the same, right? All the ones we saw so far are the same range and domain. They're all above the x-axis, and you can throw any x values in. Do they share a common point? 0, 1, yeah. Are they 1-to-1? Do you remember what 1-to-1 means? It's you have to be really careful about it, right? So like, what does 1-to-1 mean? Let's pause for different ways to say this. Every y value has 1 x value. Now there's different ways to say this, and Ms. Conroy might say it differently. Just remember though, it can't go up and down again. So do any of these functions go up and down again? Do they change? No, they either go strictly up or they go strictly. So this is strictly up, and this is strictly down. Does that make sense? It goes up and down. Now, if it changed direction, if it went up, I mean, you've seen functions that look like that. That's like, y equals x cubed. Is that a 1-to-1 function? No, because it violates what test? What's the test that it violates? The horizontal line test. Exactly. Very good. What are the asymptotes that you figured out so far? What's the one asymptote? The what? I heard the x-axis. Y equals. Exactly. So the asymptote that you've seen so far is y equals 0, which is also called the x-axis. And we already did the domain and range. Nice. Okay, so let's solve exponential equations now. This is what I would like you to remember. Common base. Even if you don't know what that is exactly, you might know already. What are the bases you're looking at right now in that question? What are the bases? There are two different bases. 9 and 27. You want a common base, so your goal is to make a common base. Is there something you can change 9 into without changing its value? Is there a way to rewrite 9? Is there a way to rewrite 9? Yeah. 3 what? 9 is 3 squared. So that's just another way to write 9. So this 9 is now here. What about 27? You can write it as what? 3 cubed. Right, so you have 3 cubed. It's just 3 cubed. We're going to write it as 3 cubed. I don't need parentheses, right? So have I changed any values? No. Have I changed any values? I have not. What do you do with powers of powers? What can you do with powers of power? You what? You multiply them. That's going to be 3 to the what? 2x equals 3 to the 3rd. So if 3 to the 2x equals 3 to the 3rd, what has to be true? 2x has to equal 3. And this is not division. This is not subtraction. It's this fact. If let's do it, a to the b equals a to the c, then what has to be true? Then b equals c. This is a rule here, and you can see it written with different letters. But if a to the b equals a to the c, then b equals c. Oh, can we solve this now? Yeah, what does x equal? 3/2. Exactly. Now, when you go for your quest to find the common base, what would you prefer, bigger numbers or smaller numbers? What's easier to deal with, generally speaking, smaller numbers or bigger numbers? Yeah, so you want to go as small as you can get. You want to go as small as you can get. So let's take a look at this one. 4 and 16, are they the same base? No. Is there something they both can be reduced to? Someone who hasn't spoken yet. What is 4? What's another way to write 4? Someone who hasn't spoken yet. 2 squared. Okay, so we have 2 squared to the 3x minus 1 equals, what's 16? Someone who hasn't spoken yet. Come on, jump out here. What is it? Yeah? It could be 4 squared, but we want the same base. 2 to the, so 2 times 2 is 4, 8, 16. So it's 2 to the 4th. 2 to the 4th. You want a common base. Now, have we changed anything? Have we changed anything? No, nothing has changed. Again, what do we do with powers of powers? You multiply. So what's your name in the back there? Yeah. Will. What's the one on the left going to be? It's going to be 2 to the what power? If you multiply that. Careful. What does it become?
2 to the 3x minus 2.
Careful. You have to multiply the 2 by everything that's up there. So it's going to be 6x minus, you had it, 6x minus 2. Yeah. So what does this one become right here? You said 3x minus 2. I know. I thought so. What does this one become? 2 to the, finish it for me. 2 to the what?
4x plus 8.
Yeah, exactly. So now you have a to something equals a to something else. So therefore, what has to be true, Will? What has to be true?
The exponents equal.
Yeah, so 6x minus 2 is equal to 4x plus 8. Now we can subtract 4x. What do you get? 2x minus 2 is equal to 8. So 2x is equal to 10, so x is equal to 5. Yeah. Now, how can you check your answers? Plug it back in. And does Ms. Conroy make you do that sometimes? Yeah, you might want to do that. Yeah, what's your question? To kind of shield you from the truth, which is you can basically do way more with math than you think. Is everything factorable? For example, a polynomial. If I just wrote a polynomial, x cubed plus 2x squared plus 9x plus 8. How many people have factored before? You know what the word factoring means? So like x squared minus 4 is equal to x plus 2 times x minus 2, right? You've seen things like that before, right? So a polynomial, what do you think? Is that nicely factorable? Is it factorable? It is. Everything is factorable, but is everything nicely factorable? No. Similarly, over here, everything can be written as the base of something else. Like, can you solve this question? 3 to some power equals 7, right? So is there a way to write 7 as base 3? Sure. Is it going to be a whole number? No. And is it going to be something you need different types of math for? Yes. Does anybody know, and you haven't done it before, does anybody know what type of math you need what type of thing you need to solve something like that? Anybody know? It begins with an L. I'll start writing it slowly. Logarithms. You're not there yet. So guess what you get to deal with? Things like this. Same bases. Yes. We love same bases. So let's try this. With your partner or the people you're right around, try working on this. Let's just do this one right here. Do that one right there. Because 6 you can't reduce. Now you don't need to, because when you see 6 and 36, you should think, oh, that's 6. So you might have written it as this first, 6 squared, but what's 1 over 6 squared equal? 6 to the negative 2. So you know that this is equal to that, so x has to be, oh look, you're done. That's pretty cool. If you can get common bases, the most complicated thing you're going to have to do is probably use the quadratic equation. I think that's the most complicated thing you're going to have to do. Okay, what about this one? Try that one. How many of you kind of did it in your head? Now, what's that first phrase I told you to deal with? What's that first phrase? Do you remember what that first phrase? Common base, right? I said find a common base. So in this case, what's your common base going to be? 3. So the first thing you can do is make the common base. So you have 3, absolute value of x plus 5 equals 3 to the what? 4th. So what can you now reduce this to? What's the next thing? If that is true, if this is true, what's the next thing that has to be true? Then what? Value of x plus 5 has to equal 4. So there's 2 ways for it to equal 4. There are 2 cases. Either x plus 5 just flat out equals 4, or what? X plus 5 equals what? Negative 4. So that would be the way you deal with that absolute value. So there are 2 answers. So x is equal to negative 1, or x is equal to negative 9. There are 2 answers to this one. There are 2 answers.
I always thought you made the 5.
Common base. I was right. Power of the same base. Simplify exponents using, oh, look at that. We used the laws. What was the primary thing we did with the exponents? What did we do? We multiplied, like powers of powers, we multiplied. And then set exponents equal using the following property. If, this is that big one right there, if a to the y equals a to the x, then x equals y. And then solve. Yay! Okay, so then you can think about by graphing. Theoretically, can you solve just about anything by graphing? Do you know how to find the intersection of 2 graphs on your calculator? No, there's an intersect function. So on your calculator can find the intersection of 2 things. So if you can graph the left side of an equation and then set it and then graph the right side, so graph this and this, What do you just find? Where they intersect. So you can work on that. So you should have right now, you should have in your notes